The primary purpose for today was to take a look back to what we were doing before midterm and to explore some of those kinds of things that were on the midterm, that were in those first 8 quizzes, and give us an opportunity to kind of reintroduce ourselves to them, and hopefully at least for some of you, hopefully recognize that what seemed hard 3 months ago isn't nearly as hard now as it was then. So getting into things like doing conversions and calculating density, those were things that we kind of struggled our way through those first couple of weeks of the semester. But after doing stoichiometry for the past month and a half, it shouldn't be nearly as difficult, because that's basically all that we reinforced when we did stoichiometry. So the actual exam itself is going to be a lot like the exams that we've taken up until this point. It's going to be broken down into subsections. It's going to be broken down into individual topics. And so for the first part of the exam, these are some of the topics that we could see. Can't guarantee we'll see all of these, but we will see definitely some of these. So things like significant figures, which again, we've been working on now all the way since January. Hopefully just by kind of sheer force of motion, we're a lot more familiar with the sig figures now than we were before. Doing conversions, calculating density, going back and looking at things like atomic structure, how many protons, neutrons, and electrons are in a given atom or are in a given ion. Using the periodic table to tell us information. Knowing the differences between ionic covalent and metallic bonding. Naming compounds. Calculating molar masses. Doing empirical formulas and other kinds of mole conversions. That was the stuff that was largely focused on in that first half of the semester. And like I said, if we've had any kind of learning growth since January, we should recognize that a lot of this stuff isn't actually that difficult to do, or at least isn't as difficult to do now as when we were looking at it originally. So in this study guide, I've got 10 pages of practice problems. Now it sounds like a lot. It is a lot, but if you looked at that list of things, I want to make sure I give you multiple examples so that we can maybe do 1 or 2 here, and then you'd have still something that you could work on as you were prepping for the exam yourself without having to redo stuff that I already did with you. So in the end, this completed guide will be in Blackboard for you to check yourself against, but we're not going to be able to do every single problem all the way through here. But let's kind of start here at the top with just significant figures. And so we see there's a couple of different things here that we can look at. One of those things is scientific notation. So how many significant figures are in this number in scientific notation? Know this, you can say it. 5. How do we know that? Well, remember, scientific notation always shows us the correct number of significant figures. So however many digits are in the number part of the scientific notation, that's our number of significant figures. Now, how about our second number here? How many significant figures are in that number? You don't want to say it. Show me on your fingers. Give me one of these. It's 4. How do we know that? Well, we have to remember our rules. When we are dealing with small numbers, none of the numbers count until we get to that first non-zero digit. Once we get to that first non-zero digit, every digit after that counts. So the trick with significant figures, in terms of knowing how many to work with, really comes down to, is there a decimal point? And if there is, we know that at a certain point, all of the numbers count, all of the numbers matter. It just becomes a matter of when do we see that first non-zero digit? So if I have a number like 9.0 here in this fourth one, both of those digits count because the 9 is a non-zero digit. So everything after it counts if there's a decimal point. But a number like 2450, here in this fourth one, that one only has 3 significant figures. Because even though we started with a non-zero digit, we don't have a decimal point. The only numbers that matter are the non-zero ones and any zero that is between the non-zero. That zero there at the end, it matters in terms of 2,450 is different from 245, but it doesn't matter in terms of the number of significant figures. Right, let's do 2 calculations here and then we'll move on. So let's do the addition, 10.1 plus 11.1 plus 8.88. The calculator tells me 30.88. The question is that the correct number of digits? And so what we have to go to is we have to remember our rules. When we add and subtract, it's not about the number of digits, it's about where the digits are. So I have 1 decimal place in the first number, 1 decimal place in the second number, and 2 decimal places in the third number. Which of those numbers is the least precise? Either of the first 2. 1 decimal place is less precise than 2 decimal places. When we do any kind of calculation, we ultimately are limited by our least precise measurement. Whether it's the least precise because it has the fewest decimal places, or the least precise because it has the fewest significant digits. In either case, 1 decimal place is what we care about. So that decimal place here is where we need to round. 30.9 would be the correct answer. And how many significant figures does 30.9 have? 3. All right, for our last one out of this particular subgroup, let's look at the multiplication here. I have 2,450 multiplied by 1.2. When I do that calculation, my calculator says 2,940. Now, calculation rule for multiplying and dividing, it's the number of digits that matters. So in this, I had 3 digits. In this, I have only 2. I'm going to round to the least precise, which would be the 2 digits. So 2,900 would be the correct result. And that number has only 2 digits, 2 significant digits. Right, any questions about any of these first 4 examples? All right, so I'm gonna leave the last 2 for you to do on your own. Again, the key will be posted in Blackboard, so all you have to do is just do these on your own, check them against the key, see if you're heading in the right direction. All right, the next grouping was the metric conversions. Now, in the metric conversions, we focused on just a few conversions overall. We looked at kilo, we looked at centi, milli, and micro primarily. Now, probably the trickiest thing about these conversions is even to you without a net. Told you I had to memorize the conversions themselves because they were going to be the kinds of things that we were going to use often enough that we needed to know them without having to look them up. So the base would be 1. And so all of these other ones are in terms of the base. So for kilo, it's 1,000. And so a conversion between the base and kilo would be 1,000 base is equal to 1 kilo. For centi, it was 0.01. So 0.01 of the base is equal to 1 centi. Or what we did more often was we turned it around and said 1 base equal to 100 centi. For milli, it was 1/1000. And for micro, it's 1 million, or 10 to the -6. So again, the way that we can look at it is 10 to the -6 base is equal to 1 micro. Or what we did more often was 1 base is equal to 1 million micro. So these were the metric units that we wanted to familiarize ourselves the most with, because in some way or another, they were going to be the ones we would use most commonly. And really, especially those top, kilo, centi, and milli. Because that was the stuff that we would end up doing things when we measured stuff in lab. Now, with these conversions in mind, if you know what the conversions are, doing the conversions themselves actually are pretty elementary now that we have a better understanding of how unit conversion and unit cancellation works. We've done the stoichiometry, we've done a whole bunch of conversion stuff. This is the same thing, just with metric conversions instead. So let's take a look at some examples here, and we'll just kind of bounce around a little bit. So if I want to convert 100 milliliters into liters, all I need to do is set up a conversion factor that converts milliliters into liters. Now, if I look at my chart here, I can put this in as 0.001 liters in a milliliter. This liters would be the base unit. And if I did that, 100 times 0.001, I would get 0.1 liters. Now again, if you don't like working with the scientific notation or the decimals, easy enough to flip those around. So instead of 0.001 per milli, you could put in 1,000 milli to 1 liter. You would have got the same exact thing. All right, let's look at this second one here. I have 625 meters. I want to turn it into kilometers. So the same thing, I got to go meters to kilometers. Using my conversion table here, there are 1,000 meters in a kilometer. My meters cancel. 625 divided by 1,000 gives me 0.625 kilometers. Right. Questions with either of those two examples? That seems pretty straightforward. Okay, what if I am not connecting to the base? So like this one here, 2,450 micrograms. I want to turn it into milligrams. At the time, I taught you that the easiest approach would be to convert to the base. So to convert to the base, 1 microgram is 10 to the negative 6 grams. And then 1 gram is 0.001 milligrams. Oh, I got that back. .001 grams per milligram. So if you do the calculation, 2,450 times 1 times 10 to the negative 6 divided by 0.001 get 2.45 milligrams. Now, seeing it now and looking at our scale, you can see that we could have done this using the numbers on the scale. We would just had to flip it. So, 10 to the negative 6, we would put on top, 0.01, we would put on the bottom. We could have done the conversion the same way in one step if you wanted. But the two-step conversion definitely works out pretty well. And so if you had to convert between units that did not have a base unit, you could convert to the base unit in each direction and use that way just fine. All right, our next piece is multi-step conversions and density. So there are a couple of examples here. For number one, we're going from squared milligrams to squared grams. The trick to this is we can use the conversion. So 1,000 milligrams is equal to 1 gram. We can use that conversion to do this other conversion if we square the conversions. If we square the conversions, 1,000 squared milligrams squared equals 1 squared gram squared. That would allow us to do the conversion directly. But I wanted to highlight number 2 here. Number 2 is a combination unit where we want to turn 525 meters per hour into kilometers per second. And so we've got to do 2 different sets of conversions. We've got to turn the meters into kilometers, and we've got to turn the hours into seconds. And where these particular calculations, conversions can be tricky for us is if I have that unit in the denominator, I have to make sure that it actually gets canceled out. So let's start with the numerator because that one's easier. I need to turn meters into kilometers. Using that metric chart, kilo is 1,000 times the base. So 1 kilometer is 1,000 meters. So my meters are going to cancel out. So I've got the kilometers. Now I want to turn hours into seconds. Now, if you don't know the direct conversion between hours and seconds, use a conversion that you do know and try to link it. So the number of seconds in an hour is 3,600. But if you don't know that, you can still connect it because you do know, okay, I don't know how many seconds are in an hour, but I do know how many minutes are in an hour. And I can divide a minute into seconds in a second conversion. Every minute is 60 seconds, or excuse me, that's true too. Every hour is 60 minutes. So I can do that first conversion, and now I've got kilometers per minute. Not quite there, but I'm a lot closer. I can then do a second conversion. Where I take my minutes and turn them into seconds. And I know that there's 60 seconds in every minute. That's gonna allow me to do that last conversion. Now I have kilometers over second, which is what I wanted. Now I just need to do the calculation. 525 divided by 1,000, divided by 60, divided by 60 again. Three significant figures, 1.46 times 10 to the negative 4 kilometers per second. So that's the thing, even if you don't know a conversion directly, chances are pretty good you do know an indirect conversion that you can then convert into what you're looking for in the first place. Time is a great example of how you can subdivide units. So let's say that you wanted to turn days into minutes. Chances are pretty good you don't know the direct conversion between days and minutes. But you can turn days into hours, and you can turn hours into minutes, and now you're okay. All right, next item here is about density. So just remember, density is mass over volume. So sometimes you can get questions like this that are very direct, where you have a mass and a volume and you just need to divide them to get the density. $65 divided by 7.85, three significant figures, 8.28. Sometimes you have to get a little bit more involved. So, like in this laboratory example, where you're doing water displacement, figure out the density. I'm going to need to figure out what the volume is by subtraction. 60.6 divided by minus 45.2, 15.4 milliliters. Now that I have that piece of information, now I can figure out what the density is by using the mass that they have given. And sometimes it's a matter of algebra. So what I would do in this situation here is, before I started plugging in and trying to solve the algebra, try to solve the algebra before you put the numbers in. I need to get mass by itself. So I look at this and go, okay, I need to multiply by volume. And so volume times density gives me mass, which is what I'm looking for. Now I can plug in the numbers and know that I'm going to get to the correct answer out of the brain. All right, let's move on to atomic structure. It's been a while since we talked about this. But looking at calcium-45, what does calcium-45 break down to atomically? So we have to remind ourselves what this isotopic notation means. So calcium would be the symbol. Ca would be the symbol, tells us what it is. 45 would be the mass number. Remember, the mass number is the protons plus the neutrons. So how do I break down this information? Well, okay, well, I know the 45 is the mass number, so I'm gonna put that in right here. I'm looking at CA. Where on the periodic table is CA? What element is that? Okay, it is in the group of alkaline earth metals, that's correct. What number is it? 20. Okay, that's its atomic number. From those two numbers, you can get all the rest of the information that we need. Because remember, the atomic number, the identity of the substance, is based on the number of protons. Since we are not told anything about charge, we can assume that if the protons are 20, the electrons are 20 as well. If this was charged in some kind of way, if we were told that this was, potassium 45 positive 2, then we know that there's a uneven relationship between the protons and the electrons. But that's not been set. Now, for the number of neutrons, the mass number is equal to 45. And that's equal to 20 protons and however many neutrons. A little bit of simple subtraction to tell us that the number of neutrons has to be 25. So for these kinds of questions, that's really all that you have to do is recognize what the element is, find it on the periodic table, and the atomic number tells you the number of protons, the number of electrons, and then the mass number minus the atomic number, that tells you the number of neutrons. For these kinds of questions, basically it's the same exercise. It's just asking you to draw a picture to go along with it. So if I'm looking at nitrogen 13, I should be able to look at nitrogen and go, okay, nitrogen's number 7. So there are 7 protons and 7 electrons. 13 minus 7 is 6. So there are 6 neutrons. And then I just need to draw a nucleus. So in my nucleus, I've got 1, 2, 3, 4, 5, 6, 7 protons. And 1, 2, 3, 4, 5, 6 neutrons. And then surrounding it all, I've got my electron shells. And now that we know something about atomic structure in terms of electrons, we can do this a little bit more precisely. First energy level would have 2 electrons in it. The second energy level would have 5 electrons in it, based upon our energy levels, the periodic table. So at midterm, we couldn't even draw this as precisely as we had. All I was looking for then was, do you have a nucleus with the correct number of particles in it? Were you able to tell me the difference between protons and neutrons in that nucleus? So, did you use like shaded in circles and open circles or something to kind of differentiate them from each other? And then did you draw the electrons on the outside and did you draw the correct number? Okay, now we've known about electron configurations. It's a little bit easier if you can see how the electrons are arranged. Right, so we did pretty well with this at the time, but for the isotopes, remember, all that we have to do with that is take the percent abundance times the mass for each one of the isotopes. Then we take all those values and we had to divide it by 100. And if you do this problem on your own, you see it, because it won't make any sense. You get a number like 2,400 for the molar mass of magnesium. You go, why is it so big? And then you'll remember, oh, wait a second. Those percentages didn't get converted into decimals. I got to divide by 100. Suddenly that 2,400 becomes 24, and you go, oh yeah. That's what's on the table for magnesium. That makes sense. For bonding here, remember the things that you're looking for as far as bonding go. For metallic bonding, you're just looking for metal signals. So, for example, this copper signal would be an example of metallic bond. It's just a metal. This copper with tin, also metallic bonding because they're just two metals together. For ionic bonding, you're usually looking for cation and anion. Easiest way to pick those out, metal and non-metal. So compounds that have metal and non-metal in them are ionic. So calcium chloride here, for example. Calcium is a metal, chlorine is a non-metal. Put them together, you're going to get an ionic compound. For covalent or molecular bonding, you're looking for just non-metals. So things like this, C10H22, carbon is a non-metal, hydrogen is a non-metal. Together, they make a covalent, a molecular compound. And then we get into stuff, periodic table, which kind of overlays a lot of that stuff that we're talking about with isotopes, along with some information there. I got 90 seconds. We're not going to be able to go through all of nomenclature at that time, but I'll make sure that we take a little bit of time on Monday to talk about it. Of the concepts out of the midterm, that was probably the most difficult non-calculation concept that we had to run into. So we'll go through these examples on Monday. So what can you do to start preparing? Well, first and foremost, if you haven't gone through and done your other assignments yet, you're going to want to go through and do those other assignments. Go back to those quizzes that we went and did at the beginning of the semester, all those paper quizzes that we had, and start exploring those. Go through this study guide. Figure out what you understand and what you're kind of struggling with. Bring that stuff with you on Monday. On Monday, we're going to talk about, I'll take your questions first. We'll talk about nomenclature, and we'll kind of start to unpack and review stuff that we started looking at after spring break. And since that stuff's a lot more recent, it's going to be a lot more familiar. So I'm more than willing to give you some time to talk about some of this rehash stuff that we haven't looked at in 3 months. So start looking, start preparing for Wednesday this weekend. It'll make your studying on Monday, Tuesday that much easier because you're not going to have to review as much. Have a great weekend.